says, we should be grateful for all the tender mercies that come into our lives. We are unaware of hosts of blessings we receive from day to day. It's extremely important that we have a spirit of gratitude in our hearts. I hope that you can cultivate that spirit of gratitude always, but especially as we get towards this conference weekend. I hope you get to have time to watch and listen to conference, because there will likely be many years in your life where you will not have as peaceful an environment to sit and watch and listen to conference. So, and remember that not every talk is for you, and that's okay. Just try to write down things, this, what the Spirit teaches you during conference is even more important than what is said during conference. Okay, so important about the dosimeters. There will be dosimeter checkout again today. Your dosimeter data is sent to you through Learning Suite. Okay, that is the way that the TAs have to give it to you. So if you do not have your Learning Suite emails being forwarded to where you regularly check email, you need to make sure that you look on Learning Suite. Questions about that? Some people say, you never got my data, and it's always there, always on Learning Suite. Right. Please double check that. Okay. Mallory here today. Okay, today we get to talk about percussion instruments. Today we'll talk percussion instruments. Monday we will do electromechanical instruments like the electric guitar, and then the carillon, and then we will do electronic music Wednesday. Next Friday we'll review for exam 3. Okay, and then the Monday, Wednesday, the last week of class will just be for trying to synthesize all of these things, pull them all together from the whole semester to prepare for your final exam. Monday and Tuesday next week, the exam 3 is still open. So you will be able to look at exams 1 and 2 during any of the posted lab times. And then Wednesday, you will actually also be able to see exam 3. Can't very well have it up there out while it's still being off. So does that make sense? So it'll be a no electronic zone. Just write down what you want to look at, or what form you had, or whatever you want to know before you come into it. Any other questions about that? Of finishing up, you guys are getting so close. So close to finishing up. All right, let's see what we can review today. All right, let's discuss the relationship between the striking position on a string and the partials that appear in the spectrum. Track of the better markers today. All right, so if you have a spectrum and you have your even tick marks here, right? And then I'm going to make them closer so I can do more lines. Okay. And your spectrum looks something like this. Where was it struck? On a fixed string. Okay, so we're missing 3, 6, and 9. That means that it was struck 1/3 the distance from one end. Remember that? But why? Why is that true? Remember why that's true? Yes.
Because it lands on the node.
Exactly. It lands on the node. Okay. So if you strike it where there is a node, then 0 energy is given to that mode in the sound. We're going to talk about that again today with the nodal lines and circles on membranes and things like that. That same idea will come into play, but now in 2 or 3 dimensions, as opposed to just the 1 dimension of the string. Questions about that? Oh, another thing I wanted to tell you, I haven't made any of those videos, help things for Unit 3. I prefer to do them for things that you need to practice, not just definitions you can look up. So, but if you feel like there are topics like that in Unit 3 that you would like to practice, you want me to work through, please email me the topics. So just say like Unit 3.9, Roman numeral number 4 or whatever. If as you're looking for it, if there's some you want me to do little videos of, that's fine. I'm not going to do the whole handout on any of them, but if there are certain topics that you think that would be very helpful for, please email me. Okay. Any other thoughts or questions? Okay, so percussion instruments is what we're going to talk about today. Okay, so what is the, well, here we go. Let's lights me on for this first. So what is the general excitation for percussion instruments? Striking of some kind, right? And then in most cases, it is striking of some kind. And then what is setting up the vibration or the oscillation? It kind of depends, right? So we'll talk about that in a minute. And then it's either the membrane, right? Or a bar, or a plate, or a bell, one of those things. Those also are tend to be the filter resonator and the varies. Okay, so the varies means we have to go into this class's idea. Okay, so let's just talk through these. Okay, so for the membrane class, what's an example of a membrane percussion instrument? I want to say membrane. Yeah, a drum, and all of the drums, anything that has a membrane hold, right? So in that case, you strike the membrane then vibrates. It has those normal modes like or natural resonances that you did like on the learning activity, right? With those modes. And so that is the oscillator, the excitation, and the filter resonator are all membranes. Okay. All right, bar instruments. My toys. They didn't bring a drum, but you see a drum in that. Okay. So here's an example of a bar. The bar just happens to be bent, right? So the excitation source was striking it, but then what determines the sound? The oscillations are flowing where? Where are the oscillations happening? In the bar. And then where, what is determining the quality of the sound, the tone color of the sound? And where is the sound radiating from? The bar. Okay. It's all of this. All right. What's an example of something in the plate family?
Xylophone.
Cymbals. So xylophones will also be bars. Okay, so the xylophones, remember, all those will be in the bar family. Cymbals, so circular things is what we need in the plate family. So cymbals and gongs. Okay. In all of those plates, it is again some kind of striking action. Then it's the plate that oscillates, the plate that is the filter, and the plate that's the radiator. And then we have the bell, which we'll talk about in a little bit, but again, there's some striking motion. Doesn't sound like a bell, but it's the metal of the bell, right? Oh, the tambourine, what would that be? That would be plates, because you have little teeny plates here. Okay, what about? Why are these different? There's something sticking around inside something. What makes it different? So there's the shape, which would be the resonator, right? The thing that's filtering it, and then you kind of tell that something smaller is bouncing around here, something larger bouncing around here, right? So that would affect the striking, right? Less sharp. Comes to that. All of these fun things. Oh, and then I brought this in. Let's look at it. This is the favorite, right? Look at that one. Range, yeah.
Where would the maracas fall under? What category here would maracas fall under?
Not really any of them.
Oh,
They're just for fun. And just so you can tell that, I mean, you know, even though this isn't one of those, right? You have something that is striking, right? So what's in there affects the sound. But then you also have the cavity, right? That then filters through. We are not going to worry about this. Okay. All right. We have professionals with us today, so we're going to let them talk. And then we'll talk some more, and then we'll be able to bring this ahead. Okay. Tell us about you, about profession.
Okay,
What do you like to do?
so I've been playing marimba for about 7 years. So I have some interest in the bars. Let's start out with a few things the professor wanted me to talk about. Was mallet shape and hardness. So So a harder mallet would probably be something like this. You can tell from the shape. They're covered in yarn. They have, especially for marimbas, you'll just use yarn. But other bell or bar instruments, you can use like plastic, brass, and rubber mallets. So something like this creates more of a sharper sound, and you'd use that in the higher key of the marimba. And something like this. Right here is more rounder, you get the fuller sound and it allows it to kind of resonate more. You use that more in the lower or using it for concert pieces. And so kind of going back, you would use this and you can hear the attack more because it's more because of how it's shaped. Another thing where you hit is important. Marimbas have three at the bottom called resonators, other like xylophones and vibraphones do too right here. So an important thing when you're playing marimba is to hit right above the resonators. So I did not bring a marimba to college, the hard instrument to find on campus. So I have a good video of somebody playing marimba. And you can kind of watch where he plays. And he's using really good mallets for this. He's kind of staying in the higher, but they're not too small to where they will create a harsh sound at the bottom. So he's kind of playing in the middle. How sometimes when he goes to hit, he hits the edge of the keys right here when he hits the sharps and the flats. That's okay as long as you're not hitting the strings because it wouldn't really resonate as much and it could hurt the marimba. So only when you're playing sharps and flats, it's okay to play.
Strings are the things that keeps the bars in place, right?
Yes. Don't want to restrict those. They're not. Another thing would be how you're playing. So a piston stroke on a bar instrument is just hitting and going straight back up to where you are. So there's about 3 techniques: 3, 6, 9, 3 inches, 6, 9. And so that kind of also affects your striking where what it sounds like. So if I'm at 3 and if I hit and I stay at 3, I'm likely to get a quieter noise. So it also affects your
So the 3 would be like 3 inches above the keys versus 6 inches above.
Yeah, I can show you.
They're very cheap.
That's okay. So probably like. And then let's rate it, but 9.
So, and if we hold this up, you can kind of see what she meant by the strings, right? So the strings are essentially the nose. That's the part of the bar that's not going to vibrate. So instead of having the ends fixed, you have points on the bars that are fixed. Okay, and what the ends will actually be antinodes because they're free, right? And you have to have nodes at those certain places. let's talk about the bars. Okay. So these are some of the bars. Okay, so you have xylophones. Oh, you have, right? Yes.
Bars, aren't they?
They're fixed at the place where they're attached and they're free at the ends. Okay. And they can also be, so this is like the chimes, right? Chimes, they're fixed kind of up here at the top, but then the bottom is free. Whereas on these, similar to that, they're kind of in a little from the ends, where they're actually gonna have to be fixed. Okay. The glockenspiel, you have the xylophone, you have the marimbas, and things. And what do the modes look like for this? Okay, so this is what I was saying. The pluses here are basically showing places where the bar is fixed. Okay, so at those places, there have to be nodes, and then the ends will be antinodes. So if they're fixed, say here at this location and that location, when you strike a single bar and you said, well, what modes are contributing, you would have this pattern and that pattern and that pattern and that pattern. So it's still mode 1, 2, 3, 4, because you have, other than the ends, you have 1 antinode, 2 antinodes, 3 antinodes, 4 antinodes. But it's just a little bit different pattern than we had before. All right, now the frequencies of these are not harmonically related. Okay, primarily that is because these bars are much, much stiffer than the strings that we talked about before. Okay, and these ones are just very flat cross section, right? They're just flat on the bottom. So if I hit it, okay, then that's kind of the sound, right? It didn't sound quite like a scale, right? It's a really cheap one. And it's been beat up probably quite a bit. But, you know, this is just supposed to be a C scale, okay? But in nice bar instruments like the marimbas, what they do to kind of tune essentially those harmonic partials to sound a little nicer and not be as, you know, twangy, is they undercut the bars. Okay, so they actually have a little bit of a different shape. Okay. So they will look like, instead of just flat on the bottom, they will actually undercut them, make them often narrower in the middle so that they can vibrate nicer, and the partials will sound more consonant than. Okay, so here is a list. If you just had this uniform bar without it being undercut, your frequencies, if your fundamental was 100 hertz, would be 100, 276, 548, 93, 1333. Okay, and those get tuned a little when you go to real instruments where they modify them. But are these harmonic partials? No. Okay, they are very inharmonic partials, but they're also widely spaced, right? They're not like 100, 112, 137, like they're not closely spaced inharmonic partials, but they are widely spaced, okay? Which for most of the bar instruments gives them an actual pitch, you know, where you could say I'm playing a scale. As opposed to a triangle. Triangle is the only indefinite pitch instrument in the bar family, because what pitch is this? Kind of hard to say. But you do know, right? If I had a larger triangle, would you expect it generally to be higher frequencies or lower frequencies? So that same idea of size still comes into play, but it's also the density and the stiffness of the material. Okay, but there, right here in the middle is my, oops, I wasn't showing you. Right here, this was when I struck the triangle. So this is some noise we have going in the room, like kind of. Okay, but then you have basically these couple of partials. So just a few partials. but they're not harmonic. Yeah, they're not even spaced. I'm gonna go bring this other guy over here so we can look at that also. Okay, so we have different partials, but they're not harmonically spaced. Okay. And if it was a nicer instrument, there wouldn't be all that fuzzy noise in between. Questions about that? Or how you would identify, oh yeah, those partials are probably from a bar instrument. Inharmonic, but they're widely spaced. Why are they inharmonic again? What's the primary reason they're inharmonic?
It is for the parts.
Right, it's the stiffness of the bar. Okay, the stiffness of the bar. All right, oh, we should see if we can see the striking location difference here on our spectrogram. Okay, so those were in the middle, striking in the middle. Now I'm going to strike on the end. Notice the difference in the timbre, right? All because of where I was striking, right? And then if I strike right on the strings, right, then you don't have nearly as much high frequency vibration. Right? They're not perfectly tied down. That's why there is still some sound, but that's just a demonstration that the striking location really does affect the tone. Okay. All right. What about tuning forks? What kind of instrument do you think they are? So they are also bar instruments. Okay, I'm going to need two hands for this, but I'm going to try to place them. Now, whenever you do tuning forks, you don't want to whack them on something hard because then you can bend them and stuff like that. So I have a little rubber mallet here. That was supposed to be 120. Spread this out a little bit to actually see it and see if it can be above the nose of the crack. Right, the projectors. Sorry. Let's try a higher one that might be above more of that noise. This is the A. So it's mostly sinusoidal, right? There's just a little bit of energy in that other third partial. That's this noise we are running today. And this one is very high, so let's move back out. Very sinusoidal. Sinusoidal means simple wave, means how many partials in the spectrum? As opposed to complicated waves. Any other question about the bar family?
So in the case of something like where they do have sort of like resonators underneath them, would you say that the filter and resonator might be those, or that's still just the bar?
Yes, so in this case, that would be the filter or resonator. The purpose of those bars is to amplify, right, certain frequencies of the sound. So that's why those bars are different lengths. So that each one is tuned to the frequency of the bar. To increase the amplitude so that it will be.
And there's the drums.
It can be in some cases. It does. Because if you have a, say, your timpani are the best example of that, right? Membranes themselves are still have inharmonic partials, but timpani are kind of tuned based on the resonance of the floor, amplifying certain partials.
So are all like the membrane bar plate and bell entrance, they're all non-periodic?
Yes, Okay, so all of these percussion instruments will have non-periodic partials, so. Tambourine, maraca. Okay. They're just making it really noisy like so. Okay. So again, for sound recording, right, if you want to faithfully record percussion sounds, you need to have a higher sample sequence, right? Because there's more high frequency energy in those than in a lot of the other instruments. All right, so this is again on the striking location. If I strike the bar right in the middle, which partials are not going to be present in the sound? Okay, so on this picture, if I was to strike right here in the middle, which partials will not be present in the sound or will have much use? All the evens. They have nodes there in the sound. Questions like that? Look at plates. Well, actually, let's go to membranes. Amber, why don't you?
Oh, it's not membrane.
It's not membrane.
No, I have no idea.
She has an interesting drum for us. Okay. All right, so here's the drum. Oh, okay. That was fun. The reason I like this video is it shows you why I could never play a snare drum. Right? And that is because the membrane is vibrating and the rate at which they move the sticks has to be in time. They have to be driving it, right? It's like if you're trying to pump a string and you're pushing when the string isn't back by you, but you're trying to push when the string's in the middle, right? That's the trick about really playing the snare drum in particular, but a lot of drums, right? You can't just hit it at any old rate you want, or you don't get good sound. Right? So if you watch this, you can see basically they have to hit it so that the membrane itself bounces the sticks back up. So it's less of really like pushing and more about controlling the feedback. Is that the way you say it? Which is an interesting thing. Okay. All right, mode shapes of membranes. Okay, this is what you play with in your learning activity. This is a little schematic type of membrane stuff that we're going to look at. Okay, so from your learning activity, let's see, is Hannah Thompson or Carson Hopman today? Okay, Kylie, Shirley, you talked about these nodal lines.
Oh,
You're Kylie Stocker. No, what? Sorry, what is your name? Stocker. Kylie Shirley is missing. Okay, everybody's missing today. All right, not all of you, but the three people that I thought I would call on are all missing today. Okay. Okay, so what do these pictures mean? What are the solid lines? Circle around the edge is the edge. Those are the nodal lines. Okay, what do the pluses and minuses mean? That they're out of phase. All the pluses are in phase together, all the minuses are in phase together, but they're out of phase with the pluses. Okay, and so, and many of you have done the Claudius-Layton labs, we'll try to do it here again. But it's this idea that in mode 1, it's called a breathing mode. It's just up, down, up, down. The whole thing is in phase like mode 1 usually is, right? Mode 2, you have half of the membrane out of phase with the other half. And then number 3 up there is like dividing it in fourths. Okay, but then in addition to just these straight nodal lines that must always pass through the center, okay, there are these circles that must be centered on the center of the membrane. And then all of those other fun, interesting combinations, many of which you saw on your learning activities. Any other comments or questions about your learning activity, things you observed? On that? Okay. Did you try the poking and striking at different places? Yeah. Did you try to poke or strike on any of the nodal lines? Should we try it? Well, we'll come back to it. We have a lot if we have time, but we're going to look at those again here on Quad. Okay, so let's answer question number 1. Okay, which of the following describe nodal lines on a membrane percussion instrument? Okay, is A true? Radial nodal lines must extend from one side to the other, passing through the middle. Is that a true statement? Okay. Circular nodal lines must form complete circles and be centered around the middle. Yes. And C is false. Okay, so when you were given pictures like those on your test and said which of these could possibly be modes on the drum head on the membrane, those are your 2 rules. A and B are your 2 rules because of the symmetry of the membrane. Okay, why do membrane percussion instruments generate closely spaced inharmonic partials? Go to that and watch it on the spectrogram. Back to the beginning. Where it's playing. All right, so this is our drum. This was the snare drum, right? So lots of high frequency energy still, right? But then if I zoom in on these lower frequencies, you can see that there are some distinct bands, but they are definitely not harmonically related. And they're much more closely spaced than for the bar family. Okay, so for the bar or for the membrane family, the oscillator and the radiator are the membrane, and then the body can be the filter. Okay. Any other questions about membranes? Striking location mallets, those are the same for all of these families. Do you have any questions about those or how they impact the tone color or timbre of the sound? Yes, please.
So answer number 2.
Yeah, so Roman numeral number 2 on membrane, right?
Question number 2.
Oh, question number 2, sorry. Question number 2, thank you. Why do membrane percussion instruments generate closely spaced inharmonic partials? Okay, they do support standing waves, so A is false. But they are not a one-dimensional system like a string. Okay, so B is one of the reasons. Okay, B is true. Sorry, no. They cannot be modeled as a one-dimensional system, so that's false. They do have resonances, so C is false. And the modal frequencies are very close related and not spaced and not related by Fn equals NF1. So that's D. And it is primarily because of the two-dimensional nature of the membrane. Okay, that whole harmonic partials thing is really only good for one-dimensional things like strings and tubes. So it's the same phenomenon, but that mathematical relationship doesn't hold.
For the membrane, the filter, the body.
Yes.
So this question's probably beyond the scope of this class, but it's more of a curiosity thing. The reason that the harmonics are sort of close, but not perfect, because drum heads kind of vibrate like a decimal function, so it's not like a perfect sine wave.
Yep. Exactly. That is right. If you solve the wave equation, you get sines and cosines, which have that periodicity, whereas for this two-dimensional system, you have the special functions. Yeah, exactly. And if you didn't understand those words, it's okay. You don't have to understand those words, but that is exactly what's going on. Okay. All right. Questions about that? Okay. All right. Trying to figure out where, oh, so that was the membranes. Okay, let's go to the plates. Okay. So cymbals, tam-tam, gongs, steel drums, right, are all examples of the plate instruments. Okay. And now I'm going to, oops. I'm going to switch out of this for a minute. And we're going to go to this camera. Hopefully it still will be up and running. This is a large quadrant plate compared to the one that you used in lab or will use today in lab. Okay. But I need somebody who wants to bow my plate and see if we can find the resonances of the plate and the nodal lines. All right, so in your lab, you had something driven, but here we're going to drive it via bowing. So just choose a nice spot here or something and bow. All right, here, let me tap it for you. That's the pitch you're trying to bow at. Oh, there you go. Starting to get the salt to jump. You can feel it starting to vibrate. Oh, there you go. You want it closer to the edge? This is an example of getting the driving frequency to match one of the resonance frequencies. It's a tricky thing. That's why I'm happy. That salt to jump around. All right, try someplace else. You can move closer to the edge if you want. Oh, there you go, there you go, there you go. So. Different frequencies. It's very tricky. Tell, right? When the driving frequency starts to equal the both. Does anyone else want to try? Thank you. Appreciate it. Okay. I'll probably just keep talking about other things while you try, and then we'll notice when you make it happen. You will sing for us. Okay. All right. So these plate percussion instruments, like steel drums, okay, all of that, they tend to have indefinite pitch, right? You don't really have a pitch for a cymbal, right, or a gong. Okay. Steel pans are one of the exceptions. Let's play a little of that music while we turn on that. Okay, so those have, you're doing great. Steel drums have little parts of the drum that have been pounded into little rings, right? That have kind of a note, right? So they've tried to make, isolate something that will resonate, at different pitches, okay? But in general, we will say that plates are plates as well as membrane are indefinite pitch. Meaning when there's music, it's not so much as play a C, play an A, it's just more like strike. Strike different places. So there's the stick slip of driving that, and then this is also a stick slip kind of thing. Get it to stick and slip just right, then you can make it throw that. Okay. Sometimes if you put it on the ground, it kind of starts. So again, that whole stick slip has to match, just to kind of get the vibration. Stick slip, kind of like that. It's a little tricky. Okay. Yeah. Let's try it. We'll see if we can make that one. So, trial and error class. Okay, so it's a stick slip on that bar is what we make it. Okay. While you guys are playing with that, we'll talk about bells. Okay. So thinking with it, we got to reach resonance. Okay. Okay. Amber brought us something called a tongue drum. Is that correct? Okay. All right.
So this is a tongue drum, it's an Aztec instrument, and basically it's kind of like a steel drum in that like it has like a hole. It also has like, you can see the two edge color front, but it has like different tones that have frequencies. And then it's not so it's in the key of C, and so there's only it goes from G to E with like about an octave and a half between.
Yeah.
That's about it.
So this would be a plate like a steel drum where they tune certain parts. They're actually like cut off so that it's separate. It's only attached to one end, so the other end would be free to vibrate. Okay, any questions about that or other interesting questions you need to know about? Okay. Right here, this was when she played for us. Right here you can see, there are partials, right? But they're very closely spaced in harmonic partials. The bell, on the other hand, has 5. A properly shaped bell will have 5 modes. It has the hum, which is not really used usually. It has the prime, which is usually the pitch that's being played. Then it has the third above that, the fifth above that, and the octave. Okay? And these are the mode shapes if you're looking at the, oh, darn it. These are the mode shapes if you're looking at the side of the bell. Okay? And then you imagine that happening all around the bell. Okay, so it's fixed at the top, free at the bottom, so antinote at the bottom, but then you get these different mode shapes. Okay. Now, if I have a bell and it sounds like this, then you say that's not a very good bell, right? Okay. But this is where we get to have fun. If I put it in the liquid nitrogen. Okay, then that will change the stiffness of the material, right? And those mode frequencies depend on the stiffness, right? Because that changes the wave speed, which will change the resonance frequencies. So if I get it cold enough, okay, that the stiffness changes, then let's see how it sounds. Does that sound more like a bell? A little bit more, needs a little bit more. It's not quite in tune for a bell. Okay, but that's why I was sitting in word choir one time, and they were singing a certain passage, and somebody said, you know, why does that certain interval always sound like a bell? And it's because when you sing these things, the prime, the third, the fifth, and the octave, those are the intervals that make up the sound of a bell. So the stiffness, the material, the size of the bells all have to be just right to get those same musical intervals. Okay? Anybody ever been in or seen a bell choir? Yeah, so they have these really amazing, expensive, fancy bells that are tuned just perfectly to have these intervals. But each bell just plays its own note, right? Okay. All right. Here is a picture inside the carillon of the carillon bells. They hang up there, and then there are little things that will strike. They strike about where the prime would have a large amplitude, okay? But this is an electromechanical instrument because the pulling of that is controlled electronically as the person pounds on the keyboard and or stomps on the pedals. So that's what's inside these are pictures from inside our carillon.
I thought it was just a mechanism based on certain things there.
So, yeah, so you think it's just purely mechanical?
Yeah.
Yeah. So ours might be purely mechanical. Some of them do have electro actuators, but yeah, you pound down on the keys to move those levers. They might be electronic assisted because it might just be so far away, but yeah. Okay. Summary, here we go. Okay. If you have these 4 different spectral frequencies, spectra with these 5 sets of frequencies, let's identify which one came from a bell, which one came from a bar, violin, membrane, and piano. Okay, so of these different kinds of instruments, which one would have these partials, 100, 200, 300, 400, which we call harmonic partials? Which of these would have those in their spectrum? Violin, the bowed string family, okay? What about this one? What do we call these kind of partials? 100, 201, 302. Slightly inharmonic partials, and they would belong to what category? Piano, okay? Because of the stiffness of the strings makes them slightly inharmonic, and the striking nature also. Okay, what about these? 100, 276, 540, 893. That would be the bar, because they're inharmonic but widely spaced. This one, 100, 159, 214, 230 would be the membrane because they're inharmonic but closely spaced. And this one, harmonic except for the minor third, is the bell. Okay. All right, so the first one is the violin. Violin has only harmonic partials. The second column is the piano, slightly inharmonic partials. The third one is the bar, widely spaced inharmonic partials. The fourth one is membrane, so closely spaced inharmonic partials. And harmonic, except for the minor third, is the bell. All right, so harmonic all except for one is the bell. Oh, we never looked at the spectrum of the bell. The last one is bell. Yep, so it goes violin, piano, bar, membrane, bell. Okay, all right. Okay, let's do number 3, which percussion instruments have a definite pitch? Yes for bars except triangles, and yes for bells. But membranes. Huh? So it says bars except triangle, membranes except timpani. numbers we did. So the answer is A and C. So E is the answer. All right, again, if you're getting a dosimeter today, come up here, please.